In this video, we're going to be talking about transmission lines. A very important and famous application of a transmission line is the cable that comes from the antenna and goes to the TV. We're going to use that example a lot and we're going to understand exactly what's happening. Now, transmission lines are also circuits. They have a generator and a load, just like normal circuits, but we study them in a very different way than normal circuits. And there are two main reasons for that. The biggest one is the frequency. They work on frequencies like 300 megahertz or very big frequencies, not 50 hertz like we're used with some normal circuits. And second, the transmission line isn't something that fits in the palm of your hand. It can be 1 meter, it can be 10 meters or something like that. To tell you what I mean exactly, let's first look at this transmission line right here. Here on the left, we have the source that can be our antenna, and then the signal passes through the transmission line, which is this part right here, and arrives to the load, which can be our TV. Now, let's say that our signal is 50 hertz, and with this information, we can calculate the wavelength, and let's see what happens. Okay, so there's an equation that says that the speed of light is equal to the wavelength multiplied by the frequency. So the speed of light is 3 times 10 to the 8. That's known, and it's always like that. And the frequency in our case is 50 hertz. Now, if we spin this formula around, we will have that the wavelength is equal to C divided by F. And if we plug this into the calculator, we will get that this is equal to 6 million meters. So this is 6 times 10 to the 6 meters. That is 6,000 kilometers. Now, let's say that we want to draw this big wave that is 6,000 kilometers. So we'll just draw a big wave. And we can see that this right here is the wavelength, which is 6 multiplied by 10 to the 6 meters. And basically what we're saying is that this wave is in our circuit. So let's just draw it very quickly, which let's say that our transmission lines is long 10 meters, okay? So if we try to draw the same transmission line from above compared to this big wave, it will look something like this. This is the transmission line, this is the load right here, okay? So it's very miniature since 10 meters is nothing compared to 6 million meters. And as you can see here, if you zoom in right here, you can see that it's basically a straight line. It doesn't matter that the actual wave is curled. If we zoom in our wires, we will just look the signal as if it's a straight line. So this is the reason that in normal circuits, for example, in Ohm's law, we would have V equals IR, and it would always be like this. It wouldn't depend on X. We wouldn't write V of X equals I of X, R of X. But at high frequencies, things change a lot. Let's take, for example, that F is 300 megahertz. Using the same formula as before, we have that lambda, our wavelength, equals 1 meter. Now, if we take that our transmission line, this right here, is 10 meters, and our wavelength is 1 meter, which is smaller, that means that literally this wave will travel like this. So it will go to this is the impedance of the generator, and it will continue going like this. So as you can see here, this is nothing but a straight line. This is a sine wave. You can see the curvature. So why this changes things a lot is because if we take the line at this point right here or at this point right here, we do not have the same voltage. Here at this point, it's bigger. It's this right here, it's the peak. And in this point here, it's zero. What this means now is that the voltage and the current will depend on position. So we will write them as Vx and Ix. So now to see how things actually work in a transmission line, what they did is they found this method called the elementary cell method of a transmission line, which what basically means is that they divided the transmission line into multiple sections where each section is delta x. That's its width, okay? And if we see things like this, we will have that the impedance is, as always, R plus j omega L But here it will have a different measure, unit measure, which will be omega divided by meter. And why is that? Because the impedance isn't the same everywhere in the transmission line. It depends on the position. That's what our divided by meter means here. And the same thing goes for admittance. We have that Y equals G plus J omega C, and it has a unit measurement of Siemens divided by meter. Now, something that you will see a lot in transmission lines and something that is very important to know is gamma, which is written like this, alpha plus J beta. And this is called the propagation constant, where alpha is the attenuation constant, and it's measured in Neper divided by meters. And this alpha basically tells us how much we will lose, how much our signal will attenuate during the travel in the line. And beta, which is the phase constant, and it's measured in radians per meters, and it tells us how much phase it will happen per meter. Another way to define gamma is the square root of the impedance times the admittance. And you needed to know all of this to arrive to the wave equation that describes the voltage here, which, as I said previously, will be the function of x, which is equal to a e to the minus gamma x plus b e to the gamma x. Now, a and b are complex numbers, and they give us the amplitude and the phase of the wave. Now, maybe you're used if you're to seeing a number like this and thinking, okay, this is just the amplitude, which means how big is the wave. But why do we need the phase for here? Well, because if it's a cosine, for example, and cosines, as you know, have this form right here, right? And if the phase is zero, the phase basically means how much a phase there is at t equals 0, right? So if there is no phase, the wave will be like this, like it's supposed to be originally. So that means that if it's a cosine wave, that it will start from the max. But if there is a phase, then it means that the wave will start from another value that is not the max. So that's why we need the phase for here. And an interesting things about transmission lines that we are not used to before is that the wave will arrive to the load, but it is not said that all of the wave will be absorbed. Some of the wave might get reflected. In some cases, which are bad cases, all of the wave will get reflected. So this part right here is what we call a direct wave, and this right here is what we call the reflected wave, which is something that is unwanted in most of the cases. And let's make it make sense right now. X is the distance in the transmission line starting from the left towards the right. So we will call it X right here. And since we are working in conditions that are not perfect, so we have resistances inside the line that will make us lose some of the signal. That means that looking at the first term right here, the bigger the X is, so the more we go towards the right, like this, the more we lose signal, so the smaller this term is. That's why this minus makes sense right here. But then you might say, like, then why does the reflected wave right here have a plus sign? Well, the reflected wave first goes from the right towards the left, in this direction right here. And since we said that we are not working with perfect conditions, that the more the wave goes towards the back, the smaller it will become because it will lose some of it because of resistances, right? Well, then it also makes sense because here, let's say that this is x equals 1 meter, and this, let's say x equals 9 meters. And since it will go in this direction right here, the more time passes, the more it goes towards the left, the smaller it becomes. So this plus sign also makes. Now we need to define one last thing before talking about the current here, which is the characteristic impedance, Z0, which is the impedance divided by the propagation constant. And we said that this impedance right here, it was not like, it's not a component like this. It's from this design right here, it's a characteristic of the transmission. It basically tells the opposition of the conductor per every meter. So divide that by the propagation constant and you get the impedance that's seen by a wave moving. So finally, we can define the current, which is also dependent on x, which is A minus gamma x minus BA gamma x. Be careful here because there's a minus sign and above there's a plus sign. This divided by Z0. Okay, so thank you for watching this video. I hope you like it. And if you have any doubts, be free to ask in the comments. And see you in the next one.